So I wanted to talk briefly about, well, some things that are relevant to what Pierre was talking about indeed. So some aspects of model-derived uncertainties in the calculation of geological phase equilibria, with reference to a new tool that Roger Powell and I are in the process of developing. So we haven't got hugely far with it. So this is a bit of a, like one of these background talks. We're setting up the background for how this will be useful when over the next few months, hopefully it comes online. Okay, so I'm going to structure the first part of this talk around a brief history of phase equilibrium modeling. Not that any of this is going to be surprising to anybody here, but just because it makes a nice structure. So let's talk ourselves through a short history of well, thermobrommetry in metamorphic petrology. So starting, of course, with single reaction thermobrometry and so geothermometry and geobarometry back in the 60s and 70s. So the aim, of course, and I do not need to tell anyone, especially anyone who's been listening to Pierre's lovely talk, that of course the purpose here is that for the first time back in the 60s, it was possible to measure one's mineral compositions, and in a quantitative sense to consider that it's possible to invert that information and obtain an estimate for a pressure or temperature of mineral assemblage development at some key stage in the history. We can discuss exactly what that means as a separate problem. So the assumption, of course, going on here is at a minimum that the rims of neighboring grains are effectively close enough to thermodynamic equilibrium that ideas about equilibrium can be useful. So here, for example, we have a classic geobarometer on which many experimentalists have worked over the years, refining and extending the calibration. And here on the right, we have the obligatory beautiful rock picture, which I have stolen from Dick White. A lovely picture that it is too. Clearly, this was a profound development in the discipline of metamorphic petrology, foundational development indeed. So the next step along our journey then is multiple reaction thermobarometry, prompted here by the idea that throughout the 70s and 80s, a number of workers were developing internally consistent data sets in one form or another, comprising mineral end member properties, where the idea there was that a very large, we were on our way to acquiring as a discipline, indeed across the petrological disciplines, a very large quantity of experimental data, painstakingly acquired, either directly on mineral end members or on reactions among end members. And then the question, of course, is how consistent is that data? Can we amalgamate that and look at that in a way that lets us, for example, see if there are any anomalies there, understand fully the uncertainties in in our understanding. I think we stuck. Going on there. Oh, let's advance manually. Okay, so the idea then with multiple reaction thermobarometry is that instead of taking our single reaction, we can then add to that a number of other reactions, adding some end members in there. We can ask, as I say, are they consistent with each other, given the uncertainties and the correlations in our model data? So, of course, when I speak of our model data, I'm talking about parameterizations that involve, for example, the enthalpy change of one of these reactions among end members, the entropy change, and of course, a lot of other stuff going on inside this value K, so our equilibrium constant. This is all a very classic equation. I don't need to explain in much detail. Of course, K accounting for the fact that in practice we are seeing a number of minerals with solid solution in which the end members are not present, are not pure within the equilibrium. And so on the right-hand side, a multiple reaction barometry calculation in which we are assuming that our temperature is 850 degrees in this particular example. And of course, if we take our observed mineral compositions and we translate those in some way, some model-dependent way into activities, and we calculate where a variety of reactions that will be relevant to those minerals would appear. Of course, they do not initially line up nicely on one pressure. In theory, they should, of course. On the right-hand side, the solid lines in a variety of colors represent the different reactions. And the solid lines, of course, are not sitting comfortably at one pressure as we would like them to, assuming that our estimate for T0 is perfect, which we will assume for the purposes of this discussion. And so then the question is, can we optimize our model parameters in a way that respects what we understand to be the covariance among those parameters, such that we can bring all of those reactions nicely to meet at a point, as in the dotted lines, the dotted equivalent of those reactions. And so that's the calculation that we're doing. It depends on having a covariance matrix among these models parameters. And when we do a calculation like this, we discover inevitably that the uncertainties are substantially larger than are commonly quoted for single reaction thermometers and barometers. That's not in any way that's not like a slight at all on the experimental work. Of course, when one is trying to develop an experimental calibration for mineral reactions, one has to make tractable the problem of characterizing the dimensions of composition along which natural systems can vary. So one will end up designing experiments in a way that somewhat simplifies that problem. So simplifies, for example, the question of all the ways in which garnet composition can vary. And so one makes the problem tractable, but in the end, natural systems capable of doing showing variability in a very wide range of compositions. Now, rather similarly, likewise, in an analogous sense, in order to do multiple reaction barometry, as opposed to single reaction thermobarometry or barometry, we're starting to require some quite considerably more sophisticated modeling, potentially. So we can't simply be interested in the amount of grossular versus not grossular in garnet, for example. We have a number of reactions that are going to involve different n numbers from the same mineral phases. And so we're starting to require composition-dependent equations of state, or x-eos, for our mineral phases that are at least somewhat sophisticated. And as soon as you have such composition-dependent equations of state, or x-eos, you can start to calculate pseudosections, which, of course, as again we all know, is where we went next on this journey. And so on the right, also stolen from Dick's paper, though I guess I am also on it, so that's fair enough, is a pseudosection. Of course, this pseudosection is, as I don't need to tell anybody here, I'm sure, is a map in pressure temperature space of the most stable mineral equilibria for our specific bulk composition. And as Pierre very nicely pointed out, one can take more or less sophisticated views of how to represent the bulk composition of one's rock sample. And the more sort of thoughtful and careful one is in assembling what is a meaningful estimate of the effective bulk composition for our equilibrium, the better. Okay, so then the idea is that one finds the field containing the observed assemblage, of course, and the size of that field broadly suggests something like a minimum model uncertainty, unless perhaps it's a very tiny field, but if it's a sort of a somewhat larger field, then that, again, in a sense encapsulates this idea that we don't know, the models are not all that perfect, right? We do not know all that well, even if we leave out the complications of when should one, when is it reasonable to apply the equilibrium assumption, how should one construct one's bulk composition, that there is an uncertainty associated with the modeling itself, which is significant, shall we say. Okay, just pausing the story for one slide to have a quick recap or a quick overview of where actually the model uncertainties come from, because that's very much worth being aware of. So the basis of the x-eos, certainly I'm taking a rather narrow view here and talking about the ones that my group develops. The basis of the x-eos is the Holland and Powell data set. So all the x-eos are built on the data set. And within the data set, things are fairly well defined. So there's an optimization of the enthalpy of formation of the end members from the elements, which is done with respect to direct calorimetry, and also a very large database of experiments on reactions among end members. And this produces a nice clean covariance matrix. Although even then one should note, because we're interested in the huge complexity ultimately of the uncertainty structure in this problem, that's this nice clean covariance matrix depends on the choices made for other parameters, which in the Holland and Powell data set are not optimized. They are based on experimental information where that exists, which is for many end members, but they are not actually optimized because that would make the problem, again, intractable. There's not really enough information to do this meaningfully, it's felt. So then on top of the data set part, which is relatively clean, we have all of the additional input that goes into constructing an x-eos, which starts as fundamentally as the choice of, in a sense, setting up the mineral, what it should look like. So what is one's choice of mixing sites, what elements will one allow to mix on those sites, how might one incorporate order disorder where it's relevant, and so forth. And we add to that then the parameters that need to be calibrated, which are so the mixing properties. So how do we handle the effect of the effect on the minerals thermodynamics of mixing end members in different proportions? And typically the parameters that we're talking about here are interaction energies. And then increasingly, as the x-eos get rather large and complex in the modern era, we have a lot of end members that actually aren't in the data set for one reason or another. So for example, if we take our models for the peridotite systems, for example, we might be talking about, say, titanium end member in kind of pyroxene. That's either there is no such end member in the data set, or even conceivably, well, we simply consider that the one in the data set is not relevant to the problem because these end members are present at maximum in very small proportions.
It's about 13 minutes.
Okay, very good. So we don't know much about correlations involved in this problem. Okay, let's go back briefly to pseudosections. So we have a couple of problems with pseudosections. One of them is that the fields can be very large. So a common temptation that people use is to say, okay, well, let's take two isoplests, so two compositional values we can measure, and find the intersection between them and use them to use that to give us one pressure and temperature. And another problem is that it's also very tempting, and it might be indeed the right thing to do, to be very literal about saying these are the phases in my rock, and this is a field on my pseudosection, and these two should line up very specifically. But that might not always be the case. Maybe that given the uncertainties involved, that all of those phases actually are meaningfully relevant given the uncertainties involved. So the new method that Roger and I are working on is going to be called AVPT+, and it will be in ThermoCalc, and it's an extension to the current AVPT method, which is a multiple reaction thermobarometry method. And the idea here is that it's a bit like the idea of taking the intersection of isoplests, but instead of taking the intersection of two isoplests, instead one essentially looks at all the isoplests and says, is there a way of doing something that is a bit like multiple reaction thermobarometry, where we say, what is the optimal position, the closest we can get to the intersection of all these isoplests, given what we know about the uncertainty structure in the modeling? And it's a combination of that approach with a pseudosection approach, in which we say we have a bulk composition, and that provides a constraint in itself. So we are essentially optimizing the intersection of all of the available isoplests rather than two. So we will see where that goes. Is it plausible that this is something that should replace then the pseudosection method? Well, it does have some nice properties. So we have an inbuilt goodness of fit test, which is something that AVPT has. So this means we can say, if we have a terrible value, the models might be dreadful, or equilibrium might be a wholly inappropriate assumption, for example. And we also sidestep the entire question of relative model assemblage stabilities. We can just say, well, we're interested in the phases that we see, and we don't hugely care. As long as we can assume that they're in equilibrium, we don't hugely care if we can find anything like an appropriate phase field on the pseudosection. It does have a small technical snag still, which is that actually this depends, in theory, this would depend on knowing the covariance matrix for all the model parameters very well, which is not really the case as yet, though we may improve our fitting methods over time. But finally, I guess the last point to come home to is that the uncertainties on pressure and temperature are still going to be large. And so, as again, if one compares it with trying to find a nice pair of crossing isoplex, we're going to find that the uncertainties are going to come out a lot larger than that. So I guess at one level, we certainly have to face up to the fact that there are a lot of model uncertainties going on, in addition to the ones that Pierre has discussed, the non-model uncertainties. Okay, so I'll just leave up some thanks to some people, given that I know we're out of time really, and also some links to our site and discussion group. Sorry, Dick, I haven't gone too far over time there.